Hey, welcome back. It's time for another deep dive into what's going on in the internet. I'm Peter Dawell,
And I'm Nora Kane.
and we're diving into the world of wireless networking. And to guide us, we've got excerpts and diagrams straight from the CCNA Certification Guide, Fundamentals of Wireless Networks.
It's like the Bible for understanding how Wi-Fi actually works.
Exactly.
Yeah.
If you're a computer science student, this is like required reading.
Yeah.
Think of it like learning the rules of the road before you can design a self-driving car.
Absolutely. You got to know the foundation before you can innovate.
Right. And speaking of foundation, I love how this chapter kicks off with a "Do I know this already?" quiz.
Yeah, a little self-assessment never hurts.
So let's jump right in. One of the first things they compare is wired versus wireless networks. Now, on the surface, it seems pretty straightforward.
Right, but there's actually a fundamental design choice at play here. It impacts everything from security to how you manage the entire network.
That's true.
Yeah.
It's not just about convenience or speed. Wired networks offer a dedicated connection, physically connected pathway, guaranteeing a certain level of stability and security. Wireless, on the other hand, relies on,
The open airwaves.
exactly, radio frequency specifically.
Yeah.
So it's less like a secure courier delivering a package and more like,
Sending a message via carrier pigeon.
okay, I like that analogy. You're hoping it arrives safely, but there's always a chance of interception or it getting lost along the way.
And that inherent vulnerability is why we have standards, like the IEEE 802.101 family. They govern how data is transmitted and how devices communicate wirelessly,
Okay, so these standards are...
creating order in what would otherwise be a chaotic free-for-all.
That makes sense.
And
I think this is where things get really interesting for computer science students who are designing the future of the internet. Like, imagine the challenges of designing standards for a world where everything is connected wirelessly. I mean, your fridge to your self-driving car.
Yeah.
How do you ensure reliability and security at that scale? It's a big question.
Absolutely.
And that actually leads perfectly into a practice question for our listeners. So what are the key differences between wired and wireless networks in terms of data transmission and connectivity? Think about it for a moment.
Yeah, take a second.
What makes wireless so unique and so different from its wired counterpart? Okay, let's move on. This chapter also dives into some wireless communication basics. And I gotta say the illustrations are super helpful.
Yeah,
They really make those concepts easier to grasp. You know how devices actually talk to each other wirelessly? It's pretty amazing.
the visuals definitely help. So
Yeah.
one key concept is that 802.11 networks operate in a half-duplex manner. So devices can only transmit or receive data at one time, not simultaneously.
It's like a walkie-talkie conversation.
Exactly. One person speaks while the other listens.
So that's why we have the potential for collisions.
Right.
If two devices try to transmit at the same time,
Exactly.
their signals clash and you get data loss.
It's like trying to merge onto a busy highway during rush hour with no traffic signals.
Oh, I can picture that. Total chaos. And how do we prevent those data pileups?
We introduce the concept of a basic service set, or a BSS. Think of it like a well-organized neighborhood of wireless devices, all communicating under the watchful eye of an access point, or AP.
Okay, so the AP acts like a...
Principal coordinator.
Got it. Managing communication between devices, preventing those messy collisions.
Like an air traffic controller.
Perfect analogy. Makes perfect sense. Now here's a practice question for you. Why is the concept of a BSS so important in wireless networking? And how does it help manage communication between devices? Think about the role of the AP and those limitations of half-duplex communication.
Take a second to think about that.
Okay, on to a question I've always had about SSIDs. The book shows this complex BSSID in a diagram. But then we see, like, my network when we actually connect to Wi-Fi. What's the difference?
That's a great question. So that BSSID stands for Basic Service Set Identifier. And it's like a unique fingerprint for each AP and its network. It's a bunch of numbers and letters that devices use to identify the network at a technical level.
Okay, but to make it human-friendly, we have the SSID.
Exactly. The service set identifier is that human-readable name you see when connecting to a network.
So it's like the friendly face of the network,
Exactly.
while the BSID is the complex code behind it.
Right.
Got it. Now, how does your device even know what networks are available? I mean, when you're searching for networks, what's actually happening?
Your device is passively scanning, listening for beacon frames that are transmitted by APs. And these frames announce the presence of a BSS and include details like the SSID security capabilities and supported data rates.
So the AP is basically broadcasting its credentials, And our devices are...
Eavesdropping to see if it's a network they want to join.
Okay, I like that analogy.
Uh,
And if a device wants to join, it sends
Use
a...
association request to the AP.
And if it's accepted.
Then the device becomes a part of the BSS and can start communicating.
All right, that makes sense. So here's another practice question for you. How does a device learn about all those available BSSs in its range? And what happens during that association process? Again, take a moment to think about that.
Yeah, give it a second.
Okay, moving on. Looking at the diagram in this chapter, it's fascinating to see how data often flows through the AP even when devices are on the same BSS.
Yeah, it's not always a direct connection.
Right, and this becomes even more important when we introduce the distribution system, or the DS. It's like a bridge between the wireless and the wired infrastructure of a network.
Exactly.
So the DS allows our wireless devices to access resources on the wider network, even if those resources are physically connected by cables.
Exactly.
Okay, and here's where things get really interesting for network management.
Yeah.
Because the DS can also map VLANs, allowing you to logically segment the network.
Yeah.
Imagine a university campus. You could have separate networks for students, faculty, and guests,
Well-
all running on the same physical infrastructure.
Exactly. VLANs act like virtual walls within a network. They enhance security and control by isolating traffic between those different groups.
So VLANs are a pretty powerful tool for network administrators. Now for our listeners, what are the advantages of using a distribution system in a wireless network, and how does it relate to VLANs? Think about the benefits of network segmentation and how you can integrate those wired and wireless devices. Take a moment to consider this.
Think about it for a second.
All right, building on that concept,
Yeah.
the book reveals something pretty cool. Multiple SSIDs. Multiple SSIDs. So you can have more than one Wi-Fi name for the same network.
Exactly.
Why would you want to do that?
Imagine you want to offer different levels of access or create separate networks for different purposes. Remember our university example?
Okay.
You could have a student SSID with full access, a faculty SSID with restricted access to sensitive data,
Uh-huh.
and then a guest SSID with limited access and bandwidth.
So a single AP can actually support multiple SSIDs, each mapped to different VLANs. That's a clever way to create logically separated networks within the same physical infrastructure.
It is.
It's like having multiple apartments in the same building, each with its own separate entrance and security measures.
Yes.
I like that analogy. So for all our listeners out there, imagine you're designing a network for a university campus. How could you use multiple SSIDs and the concept of ESS, which we'll get into more detail about later, to provide different levels of access and coverage? It's a good one to think about.
Yeah, take some time with that one.
Now, the book also touches on some alternative wireless topologies that are less conventional,
Right.
but still very intriguing. You see things like the ad hoc independent basic service set, or IBSS.
The IBSS is a truly independent network where devices communicate directly with each other without a central AP. Think of it like a group of friends sharing files directly between their laptops without a Wi-Fi router.
Ah, so it's like a mini self-organizing network party.
Exactly.
I like it. And then we have the various bridging techniques, repeaters, workgroup bridges, and mesh networks.
Right. These are all ways to extend coverage or connect locations that are far apart.
It's like wireless networking is all about finding creative ways to overcome the limitations of distance and physical connections.
Yeah, you could say that.
Yeah. And each technique has its own strengths and weaknesses depending on the specific needs of a network.
Right.
Here's a question for everyone listening. When might you use a repeater versus a workgroup bridge to extend a wireless network? And what are the trade-offs involved? Remember, a repeater simply amplifies the existing wireless signal to reach further, while a workgroup bridge lets you connect a wired device to a wireless network. Take a moment to compare and contrast these two techniques.
Yeah, think it through.
Okay, let's shift our focus to the frequencies that make all of this wireless magic possible. The 2.4 gigahertz and 5 gigahertz bands.
Yes.
I love how the book visually lays out those channels within each band. It shows how some channels overlap while others don't.
It's like a map of the wireless spectrum.
Exactly.
Yeah.
And choosing the right channel is really important for performance.
It is. Using overlapping channels can lead to interference, which degrades your network performance. It's like trying to have multiple conversations in the same room. It becomes hard to understand anything.
So choosing non-overlapping channels is like finding those quiet spots on the radio dial.
Exactly. Where you can enjoy your music without static or interference.
Perfect. Now, for even greater bandwidth, we have channel bonding, where you combine multiple channels to create a wider data pipeline.
But not all devices and APs support that.
It's like upgrading from a 2-lane road to a 4-lane highway
Exact.
for those data-hungry applications. Now, here's a final practice question for this section. Why are there multiple channels within a wireless band, and what considerations should you make when selecting a channel for a network? Keep in mind the impact of overlapping channels and those potential benefits of channel bonding. Take a second to think about it.
Give it some thought.
We've covered a lot of ground today, from the fundamental differences between wired and wireless networks to all those different techniques used to extend coverage and manage network traffic. I think we've all gained a deeper appreciation for just how complex wireless communication really is.
It definitely is.
But this is just the beginning. Our journey continues next time when we'll explore the evolution of Wi-Fi standards, delve into the intricacies of network architecture, and see how all these concepts come together to create that seamless wireless experience we take for granted. Stay tuned.
We'll be back.
Welcome back to our exploration of wireless networking. I'm Peter Dawell.
And I'm Nora Kane.
Last time we really dug into those foundational concepts of wireless communication. From the key differences between wired and wireless to the roles of BSSs and APs.
We even touched upon how a distribution system bridges the gap between wireless and wired networks, and of course those VLANs that can segment a network for better security and management.
Right. And to really understand where we are today, we need to look back at the evolution of Wi-Fi standards.
Absolutely.
Chapter 1 of our CCNA guide has this really helpful table outlining the various 800 to 802.11 amendments and their corresponding data rates. It's amazing to see how far we've come.
It is.
Started with that original 802.11 standard back in 1997, offering a measly 2 millizacs, to the latest amendments like 802.1ICC and 802.101X, promising gigabit speeds.
It's incredible how quickly technology advances.
I know, it's mind-blowing.
Yeah.
But it's not just about speed. These amendments introduce new features and capabilities that really shape how we use and experience wireless networks.
Right.
So the book mentions amendments like 802.11b, 802.11g, 802.11n, and so on. What's the significance of these different amendments?
Well, each amendment represents a step forward, often introducing improvements in speed range and efficiency.
Okay.
So, for example, 802.11b was a significant leap from the original standard offering speeds up to 11 MB.
Okay.
Then came 802.11g, which maintained backward compatibility with 802.1 MB.
That's important.
Very important. It means older devices can still connect to newer networks, albeit at slower speeds. It ensures a smoother transition as technology evolves.
Makes sense. And then we had 802.11n, which was a game changer.
Yeah.
It introduced MIMO technology.
Yes. Multiple input and multiple output.
Right, for even faster speeds and improved reliability.
Right.
Can you explain MIMO in simple terms?
Sure. It basically uses multiple antennas to transmit and receive data,
Okay.
creating multiple pathways for the signal to travel.
So it's like having multiple lanes on a highway.
Exactly. More cars can travel simultaneously without causing congestion.
I love a good analogy. And what about 802.11ac and 802.11ax? Those seem to be the current frontrunners in the Wi-Fi world.
They are 802.11sc operates in the 5 gigahertz band.
Which is less crowded.
Yes,
Okay.
offering significantly faster speeds and greater bandwidth. And then 802.11ax, also known as Wi-Fi 6, builds upon those advancements, introducing features like OFDMA and MU-MeMo.
Who are those two?
They provide even better performance in dense environments with multiple devices.
So it's like a constant race for faster speeds, greater bandwidth, and more efficient use of the airwaves.
Exactly.
To simplify things for consumers, the Wi-Fi Alliance introduced a generational naming convention.
Yeah.
So instead of remembering all those cryptic 802.11 amendments, you can just look for Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, and so on.
Much easier.
So Wi-Fi 6 is basically the simplified name for 802.11ax. Got it.
Yeah.
It makes it easier for consumers to understand what they're getting.
Absolutely.
Now, let's say you're setting up a new wireless network. What factors should you consider when choosing between those different 802.01 amendments for your devices and APs?
Well, you need to consider your speed requirements, your budget, and the types of devices you'll be connecting.
Okay.
Do you need the blazing fast speeds of Wi-Fi 6, or will an older standard suffice? It's about finding the right balance between performance and cost.
Makes sense.
Yeah.
Now, I find it interesting that the book also delves into alternative wireless topologies, configurations that go beyond the typical BSS and ESS setups.
Right. These alternative topologies offer unique solutions for specific scenarios. For example, the Independent Basic Service Set, or IBSS, is a peer-to-peer network without a central AP.
Right, so the IBSS is like a spontaneous gathering of devices
Exactly.
forming their own little communication, but perfect for like impromptu file sharing or a gaming party.
Exactly.
And then we have the various bridging techniques.
Right.
Repeaters, workgroup bridges, and mesh networks. All clever ways to extend coverage or connect locations that are far apart.
It's like wireless networking is all about finding creative ways to overcome those limitations of distance and physical connections.
You could say that each technique has its own strengths and weaknesses depending on the network's specific needs.
Absolutely.
Here's a question for everyone listening. When might you use a repeater versus a workgroup bridge to extend a wireless network? And what are the trade-offs involved? Remember, a repeater simply amplifies the signal to reach further, while a workgroup bridge lets you connect a wired device to a wireless network. Think about the specific use cases and the limitations of each technique.
Take your time.
Moving on, let's talk about the frequencies that make all of this wireless magic possible. The 2.4 gigahertz and 5 gigahertz bands.
Yeah, those are the two unlicensed frequency bands that most Wi-Fi networks operate within.
And the book provides a visual representation of how the channels within each band are laid out, showing which ones overlap.
Right.
That visual representation is really key to understanding how interference works.
It is. Using overlapping channels is like having multiple conversations happening in the same room. It's hard to understand anything. Non-overlapping channels create those clear pathways for communication.
So choosing the right channel is like finding that quiet spot on the radio dial.
Exactly.
And for those who need even more bandwidth, there's channel bonding,
Yes.
combining multiple channels to create a wider data pipeline.
But remember, both the devices and the AP need to support it.
It's like widening a highway to accommodate more traffic.
Exactly.
Here's a question for you. Why are there multiple channels within a wireless band? And what considerations should you make when selecting a channel for a network? Think about the impact of overlapping channels and the potential benefits of channel bonding.
It's a good one to ponder.
We've covered a lot of ground in this segment, exploring the evolution of those Wi-Fi standards and diving into the world of alternative topologies and those frequency bands.
We have.
But there's still much more to uncover. In the next part, we'll shift our focus to network architectures and design principles.
Looking forward to it.
We'll see how all of these concepts come together to create those real-world wireless networks. Welcome back to the Deep Dive. It's Peter Dawell here.
And I'm Nora Kane.
We've been on quite a journey exploring those fundamentals of wireless communication and the evolution of those Wi-Fi standards that shape how we connect.
It's been a wild ride.
It has. Now it's time to shift gears and look at the bigger picture, how all these components come together in real-world networks.
Okay.
And Chapter 2 of our CCNA guide dives into Cisco wireless architectures.
Right.
This is where things get really interesting, I think, for anyone who wants to build or manage networks. It's like going from learning the alphabet to actually writing a novel.
Absolutely.
We're taking those basic building blocks and seeing how they create these complex systems.
Right.
So the chapter starts by introducing the autonomous AP architecture, which feels pretty familiar.
Yeah. Autonomous APs are those self-contained units we often see in smaller networks.
Right. Each one operates independently, managing its own settings and client connections.
Exactly. It's a simple approach, perfect for homes or small businesses, where the network demands aren't too complex.
But I imagine as networks grow and, span multiple buildings or even cities managing hundreds of these individual APs would become a nightmare.
It would. Trying to configure and troubleshoot each AP separately wouldn't be efficient at all.
So what's the solution?
That's where the cloud-based AP architecture comes in.
Okay, so we're talking about managing those APs from a central location in the cloud.
Exactly.
That sounds like a major upgrade for scalability.
It is. Imagine a large enterprise with APs scattered across various locations. A cloud-based architecture lets you manage them all from a single platform.
So it simplifies everything, configuration monitoring, troubleshooting.
Exactly. It's like having a central command center for your entire wireless network.
No more running around to each individual AP to make changes.
Exactly. And with the cloud handling all the heavy lifting, IT staff can focus on more strategic tasks.
So cloud-based AP architecture definitely wins points for efficiency and scalability. But are there any other architectural models out there?
There are. The book introduces the split MAC architecture, which offers a unique approach to managing and controlling APs.
Split MAC. That name sounds intriguing. What makes this architecture different?
In a split MAC architecture, the functions of an autonomous AP are divided between the AP itself and a central controller,
Okay.
known as the Wireless LAN Controller, or WLC.
So instead of the AP handling everything, some tasks are delegated to this WLC.
Exactly. The AP handles real-time tasks like transmitting and receiving data, while the WLC manages things like security policies, client authentication, and roaming.
So it's like a division of labor,
Precisely. The AP focuses on connectivity, while the WLC acts as the brains of the operation.
making sure everything runs smoothly and securely.
Exactly.
That makes sense.
Yep.
So we have autonomous APs, cloud-based APs, and split MAC architectures. Is there a best approach?
It really depends on the specific needs of the network. Autonomous APs are great for those small, simple networks. Cloud-based architectures excel in large distributed environments, and SplitMac offers that balance of centralized control and efficient AP operation.
So it's like choosing the right tool for the job. You wouldn't use a hammer to screw in a light bulb.
Exactly.
Now, the book mentions something called CapWAP. What role does CapWAP play in all of this?
CapWAP stands for Control and Provisioning of Wireless Access Points, and it's the protocol that enables communication between the WLC and the lightweight APs in a SplitMac architecture.
So it's like the language they use to talk to each other.
You could say that the AP and the WLC can be physically separated, but CapWAP allows them to stay connected and communicate effectively.
So CapWAP creates a secure tunnel between them.
It does, allowing the WLC to control and configure the AP even across vast distances.
It's like having a virtual umbilical cord connecting them. And to add another layer of complexity, the book discusses centralized and distributed deployments when it comes to the WLC. So a centralized deployment involves placing the WLC in a central location within the network.
This is common for smaller networks where all the APs are relatively close to the WLC.
It's like having a single control center for your wireless operations.
Exactly. But in larger, more distributed networks, you might opt for a distributed deployment where you have multiple WLCs spread across the network, each managing a subset of APs.
So it's like dividing your kingdom into smaller provinces, each with its own local ruler to better manage a vast territory.
Exactly. This can improve performance and scalability by reducing the load on any single WLC.
I have to admit, all this talk of architectures and deployments is a lot to take in.
It can be. But remember, you don't need to become a wireless architect overnight. The key is to understand those different approaches and how they apply to different network scenarios.
Right. It's about building that foundational knowledge and recognizing that different situations call for different solutions.
Exactly.
And with a solid understanding of these fundamentals, you'll be well equipped to navigate the ever-evolving world of wireless networking. Well, that brings us to the end of our deep dive into wireless networking fundamentals. We've covered so much ground, from those basic principles of wireless communication to the complexities of network architectures. We've seen how data travels through the airwaves, the importance of standards of protocols, and the various techniques used to extend coverage and manage those wireless networks. And we even tackled some thought-provoking practice questions along the way to really test our understanding of these concepts. But as we wrap up this deep dive, I want to leave you with a final thought. Given our increasing reliance on wireless networks, what new challenges and innovations do you think we'll face in the future of Wi-Fi? Will we see even faster speeds and greater bandwidth? Or entirely new ways of transmitting data wirelessly? Will Wi-Fi become so ubiquitous that it seamlessly integrates into every aspect of our lives, powering everything from smart homes and cities to self-driving cars and wearable devices? The possibilities are truly endless. As technology continues to evolve at an unprecedented pace, the future of wireless networking promises to be both exciting and transformative. So keep exploring this fascinating field. Delve deeper into those technical details, and perhaps even consider a career in wireless networking. The opportunities are boundless. Remember, the journey of learning never truly ends. There's always something new to discover, a new challenge, to overcome, a new innovation to explore. So keep that curiosity alive, keep asking those questions, and keep pushing the boundaries of what's possible. The world of wireless networking awaits, and you have the potential to shape its future. Thanks for joining us on this deep dive into wireless networking. Until next time, keep exploring, keep learning, and keep those Wi-Fi signals strong.